distinct stages that you might have observed in this video. One is when the concrete is uncraked and there is a pure elastic stage. At this stage it corresponds to loads much lower than the ultimate, and concrete remains uncraked in compression as well as tension, and the behavior of steel and concrete both is elastic. When there is no crack, concrete is also elastic, steel is also elastic. There is no crack, everything is in elastic stage. This is stage number 1. You have seen this stage in the video. Then there is a second stage when concrete is cracked but only on tension side. There is no crack on compression side. So with increase in load, you have seen in the video that concrete cracks in tension but remains uncracked in compression. So it depends on the stress on the compression side. If the stress due to the load that you have applied on the compression side is less than 0.45 F'C, concrete on the compression side will remain elastic. I hope this is clear now. On tension side, everything is gone. Concrete is gone on tension side. But on the compression side, it will depend on the load. If the load is such that stress on the compression side in the extreme fiber is less than 0.45 F'C, concrete will remain elastic on the compression side, inelastic and cracked on the tension side. And steel is still elastic on the tension side because it has not reached its heat limit. So steel on the tension side and concrete on the compression side, they remain in elastic stage. Steel on the tension side and concrete on the compression side. This is stage number 2. In stage number 3, which is the ultimate stage, concrete is cracked in tension, which is already cracked in the stage number 2. But now concrete in compression and steel in tension both enters into inelastic stage. The steel has crossed its yield limit and concrete has crossed 0.45 F'C. Concrete has crossed the limit. The stress in concrete is now more than 0.45 F'C, so it is inelastic. It has entered into an inelastic stage. And steel on the tension side, because it has crossed its yield limit, so it has also entered into an inelastic stage. At collapse, what happens? Steel will yield and concrete will crush on the compression side. Steel will yield on the tension side and concrete will crush on the compression side. Now, it will depend on the amount of steel, whether the steel yields first or the concrete concrete on the compression side crushes first. It will depend on the amount of steel, which we will see in the next slides. If we look at the behavior of stage 1, so the behavior of stage 1 is such that there is no crack on the tension side in concrete. Okay. The strain diagram is like this and the stress diagram is like this, and stress is proportional to strain at every depth. Fc is stress in concrete. Ft is stress in concrete, but this is tensile stress and this is compressive stress. And if we look at the stress strain diagram of concrete, not of steel, so we can plot a stress strain diagram of concrete like this. This is the stress and this is the strain. So Fc, you know that the stress and strain diagram of concrete will be like this, because the concrete tensile strength is much smaller than the compression strength. So if Ft, which is the tensile stress, this tensile stress is equal to this point on the stress strain diagram, and the compressive stress Fc is here on the stress strain diagram, which is in a very initial stage, and stress and strain both are linear and elastic. Okay, please. So the load on the member is such that FC is here and FT is here. FT is such that it is almost equal to the modulus of rupture. You know that it is equal to 7.5 times FMC. And any value of FT greater than this will cause a crack in the beam. Okay. So this is a very useful slide for the purpose of calculation of MCR. MCR is a moment, cracking moment. It is called the cracking moment, and this is the capacity of the beam corresponding to the modulus of rupture when tensile strength is equal to modulus of rupture. And this M crack is used in many equations in the pre-stress concrete as well as in the calculation of deflection in reinforced concrete. Calculation of forces. In this case, if you look at the stress diagram, so this is a triangle, this is also a triangle. So 1/3 from this side and 1/3 from this side. So the moment arm will be 2 by 3h. And because you have a zero stress here and FC here, so average stress will be FC divided by 0 plus FC divided by 2, it will be 0.5 FC. And the area, you know that triangle area is B times H by 2. So it will be B into 0.5 H. So C is equal to 0.5 FC into B into 0.5 H. Similarly, T is equal to 0.5 FT into B into 0.5 H, and T must be equal to C. You know this very well. C must be equal to T. Okay. So now if C is equal to T and then FC is also equal to FT, so M can be calculated. From the lever arm, either C into 2 by 3H or T into 2 by 3H is one and the same thing. So if C times 2 by 3H is taken, 0.5 FC into B into 0.5 H is equal into 2 by 3H. This will give you 1 by 6 FC BH square. If FC is equal to FT, okay, so modulus of rupture or the tensile stress. The tensile stress or the tensile stress can be calculated from the 6m divided by BH square, or M crack can be calculated from this equation as well. ठीक है क्या नहीं? आप समझ रहे हैं इस बात को? If there is any question, you can ask question. And from the other equation on the other side, because this is a stage where the concrete and steel both are in elastic stage, so the flexure stress formula is applicable, and from this flexure stress formula, FC is equal to FT is equal to MY by I or MC by I, where C is equal to 0.5 H, you know this, and I gross is equal to BH cube by 12, and FC is equal to FT 6 MB. So both the equations will give you the same results. This is a conventional approach that we follow for the design of beam, and this is a non-conventional approach, but we use this approach in flexure stress formula for material which are in a stage when the stress is and strain are linear and elastic. Okay. So if you want to calculate the cracking moment capacity now, you just have to substitute the from this equation 6m by bh square, or from this equation you can calculate m by putting ft is equal to 7.5 prime c. At fc t is equal to fr, where modulus of rupture is equal to 7.5 prime c, cracking moment can be calculated from this equation as fr into ig divided by 0.5 h, fr into bh square divided by 6, and fr can be calculated from 7.5 prime c, square root of f prime c. I hope this is clear to all of you. So if you want to write down these equations, you can. So with the help of this equation, you can determine the cracking bending moment capacity of any beam. If you know the section of the beam and the concrete strength, you can calculate the cracking moment capacity, which means that you can calculate the stage of the loading stage at which the beam will crack. Okay? So this is stage number 1. So in stage number 2, Stage number 2 is such that concrete has cracked on the tension side. Concrete is cracked. On the compression side, the load is such that stress in concrete on the compression side in the extreme fiber is equal to 0.45 F prime C. So if this is the case, on the stress strain curve of concrete, you are here at this location. So the behavior is still somehow linear and elastic. Okay. On the tension side, the steel has been stressed. The load is such that stress in steel is equal to 0.5 times Fy. Okay, the load is such that, and the amount of steel is such that this is possible that when Fc is equal to 0.45 Fc, so the stress in steel is 0.5 Fy. If this is the condition, then equations can be written for this condition, which are shown on the next slide. And if F is equal to 0.5 Fy on the stress strain curve of the steel, you are here at this point. So it is still in linear elastic stage. Since there is a concrete has cracked on the tension side, so on the strain diagram, the strain diagram is like this. You can see the strain diagram. Okay. Strain in steel is equal to Fs divided by Es, and strain in concrete is less than 0.003 because 0.003 is here when concrete has reached its compression strength or has crossed its limit of F prime C. So 0.03 is here and we are here. So strain in concrete is less than 0.003. Clear? Corresponding to this stage, equations can be written now, but flexural stress formula will not be applicable now. So we will use the equations of statics. C is equal to T and the bending moment. C is now 0.5 times C into BC, where C is the neutral axis depth and B is the width, because this is the area to which the green area to which concrete has been stressed by the load. So you can see that B is the width and C is the depth of this block, this compression zone or completion block. So the area is BC, and the stress is again, because it is a triangular stress variation, so 0 plus Fc divided by 2, 0.5 Fc into BC. Okay, so C is equal to 0.5 Fc into BC and T is equal to ASFS. And since this the total length, the total depth of the beam from the top of the beam to the centroid of the tension steel is D, effective depth D. Okay, and this neutral axis depth is C in this case. So this is 1/3 of C. So lever arm will be equal to D minus C by 3, because this total is D. So minus C by 3, this is D minus C by 3. If you want to write down the equations, so you can write down the equations like C is equal to T for summation of Fx is equal to 0, which will further, by substitution of C equal to half Fc BC and T is equal to ASFS, will yield the value of C, neutral axis depth, equal to 2 ASFS divided by FCB. And since you know that Fs is equal to Fs is equal to what? Fs is equal to strain in steel into Es, and Fc is equal to strain in concrete into E into concrete, E of concrete. And you know that there is a term called as modular ratio, defined by the ratio of modulus of elasticity of steel to the modulus of elasticity of concrete. So if that is replaced by N, then Fs is equal to N times Fc. Okay. So because strains will be equal, strains in concrete and strain in steel will be equal, so they will be cancelled out. For perfect bonding of steel and concrete, this is one of the basic assumptions And this assumption is quite true up to the final failure stage. Because if there is no perfect bonding between steel and concrete, so the load will not be transferred to steel, or stress will not be transferred to steel from concrete. Okay? So, due to perfect bonding between steel and concrete on the tension side, strain in concrete at that level where the steel has been provided must be equal to the strain in steel. So, strain in steel equal to strain in concrete here at this location. If you draw the strain diagram here at this point, strain in steel must be equal to strain in concrete. So, they will be cancelled out. Okay. So, C is equal to 2AS Fs divided by FCB, and since Fs is equal to NFC, so by substituting the value Fs by FC equal to N, C is equal to 2AS N divided by B, and N is equal to the modular ratio, which is ES divided by AC. So, neutral axis depth can be calculated provided you know the amount of steel AS, because everything else is known in this equation. N can be calculated very easily because the modulus of elasticities of steel and concrete are known to us. And if they are not known to us, we can calculate at least the modulus of elasticity of concrete from the equations discussed in the previous lecture on the material. The steel modulus is already known to us. So, and in this equation, you know that A is also an unknown, because A is we want to calculate. So, A is not known to us. B we can assume width of the beam. So, C cannot be calculated unless AS has been calculated. And from the equation of the bending moment or the couple, M is equal to T into LA, and you know that lever arm as discussed earlier is equal to D minus C by 3 ASFS, and from this AS can be calculated M divided by Fs D minus C by 3. And since C is unknown in this equation, so AS cannot be calculated. So, from the, you know that from the trial and success method or hit and trial method, you can assume a value of C, you can calculate A, substitute the value of AS in this equation, calculate C, and from hit and trial you can calculate AS. So, this is corresponding to stage number T2, and this was basically the procedure which was followed for the working stress method before the ultimate strength design method. This was the procedure for working stress method. This procedure was followed. किस तरह वो 0.45 F प्राइम सी था, वो तो हमने तो वो वैल्यू डाली नहीं है इसमें. ये एक है FC, और आप देखें FC इज इक्वल टू 0.45 प्राइम सी. समझ गए आप? ये अलग चीज है. FC की वैल्यू 0.45 प्राइम सी वो हमने डाली नहीं है इसमें. और इसका जो स्ट्रेस, एवरेज स्ट्रेस आप मालूम करेंगे तो ट्रायंगुलर के लिए 0, ये तो आपको पता है 0.5 से होगा. सो दिस इज द कैलकुलेशन करेस्पॉन्डिंग टू स्टेज नंबर 2. ओके, एंड स्टेज नंबर 3. Stage number 3 is a stage where concrete also cracks now on the compression side, crushes on the compression side. Concrete on the tension side is already cracked. Now, the conditions are such that the load is such that the load which has been applied, and the amount of reinforcement which has been placed here, and the strength of concrete, all these are such that a given load will stress this member into such conditions. ठीक है जी? So the conditions are such that strain in concrete is 0.003. Strain in concrete is 0.003. And on the stress strain diagram of concrete, 0.003 is a stage which is here, this stage, which means that the stress in concrete and the extreme fiber has already crossed the limit of F prime C. It has passed this stage, so concrete has been crushed. Concrete is crushed on the compression side, We are not here. In the extreme fibers, when strain is 0.003, so it is not possible that Fc is equal to F prime C. This is not possible. Because corresponding to 0.003, Fc is less than F prime C, which means that this limit has been crossed. Okay? And Fc in another fiber of concrete, not in the extreme fiber, is at a stage where this stress is equal to F prime C. But then the strain corresponding to this is less than 0.003. The strain at this is less than 0.003. Okay? Okay, now on the tension side, and now you can see that the stress in concrete at every depth is not proportional to strain. Stress is not proportional to strain. Okay? Stress variation is parabolic and the strain variation is triangular distribution, and this is parabolic. The steel variation is such that the steel state is such that steel has been stressed to its yield limit. So you are here on the stress strain diagram of the steel. Fs is equal to Fy. Fs is equal to Fy. Okay. And the strain in steel is the yield strain, which can be calculated very easily from Fy divided by Es. Understand? So if you want to write down equation for this stage, there is a difficulty. And the difficulty is that Fc variation is parabolic. So what will be the resultant Fc? This is not known to us. In the triangular distribution, 0 plus Fc divided by 2, Fc by 2 we can very easily. If this is a rectangular distribution, then average stress is Fc. And in the triangular distribution, average stress is Fc plus 0 divided by 2. But in this case, when the variation is parabolic, so we do not know how to calculate Fc, average Fc, for the calculation of the resultant force C. Compressive stress C is equal to stress into area. Okay? And this average stress or average strength is not known to us now because there is a parabolic variation. Had it been a triangular distribution or a rectangular distribution, we would have calculated this very easily. But due to this variation, this is a problem in the calculation of Fc. Okay? So for this purpose, there are different models available in the literature. There are researchers who have approximated this calculation of Fc, and the most famous, it is from Whitney's equivalent rectangular stress diagram, which is widely used for the calculation of compressive stress at this stage. But there are also other models available. If you are interested, you can go through the literature, and there are several other models also available for the calculation of compressive stress C at this stage. Pure parabolic is also available. Pure parabolic, but it is very complicated equation. Okay. For the design purpose, however, this approximation is enough, and we can follow this for the design purpose because there are many uncertainties. Even if this pure exact equation is followed, still there are many other uncertainties that we will have in our final design. So, keeping in mind all those uncertainties, the Whitney's stress diagram is quite acceptable, and the Whitney stress diagram is such that it is a rectangular stress now with the compression block depth not equal to the neutral axis depth C. Okay? Because C is this depth, neutral axis is this. So according to the Whitney's equivalent stress diagram, the compression block of the rectangular stress block will be equal to small a times beta 1 C, and of course beta 1 shall be less than 1. Okay? So this is an equivalent area which best represents the parabolic area. And the stress on the compression side in the extreme fiber has been approximated by 0.85 F prime C. Why? Because F prime C limit has already been crossed. When the strain is equal to 0.003, the stress in the extreme fiber cannot be equal to F prime C. We have seen this in the previous slide in the stress strain diagram. So F prime C, Fc will be equal to 0.585 F prime C when the strain is 0.003. And from the rectangular stress distribution, now it is very easy because we will use the average stress. For rectangular stress distribution, you know that average stress is equal to the stress given on the diagram, that is 0.85 F prime C. So 0.85 F prime C is the stress now. Okay, and the area is now A, not the rectangle total area, which is the green area, but a reduced area, A times this is A and this is B. So the reduced area A times B is the area on which the stress 0.85 F prime C is being applied. Okay, so compression stress will be equal to C is equal to 0.85 prime C into AB, and T is equal to SFY, and the lever arm is D minus A by 2. From the equation, C equal to T 0.85 prime C AB, and this you can calculate small a and you can calculate A's. You know the rest of the things are very clear to you. You studied these things in your undergrad course. Now, this is one of the important slides in this lecture that we have now derived the equations, but how to determine the capacity of the section where the reinforcement has been placed. So, according to the strength design method of the ACI 21.2, the nominal flexural capacity of R chamber shall be calculated from the conditions corresponding to stage 3. यानी कि आप स्टेज 1 और 2 के करस्पॉन्डिंग कैपेसिटी नहीं मालूम करेंगे। एसीआई कोड कहता है कि अगर आपने अल्टीमेट स्ट्रेंथ डिजाइन मेथड को फॉलो करना है तो आप स्टेज 3 के करस्पॉन्डिंग कैपेसिटी मालूम करेंगे और उस कैपेसिटी को आप अपने कैलकुलेशन में इस्तेमाल करेंगे। क्लियर? अब जब आप स्टेज 3 के मुताबिक करेंगे तो आपने यू हैव सीन द वीडियो ऑफ द बीम, देयर आर सेवरल स्टेजेस. The beam can take more and more load. Finally, the concrete crushes, and even after the crushing, there is a capacity of taking load. So, which should be the final capacity that we will use in our calculations? This is a question. Which should be the end of the capacity, and a cutoff line beyond which we will not utilize the capacity of the beam in our calculations. Though there is actually there will be capacity, but for the calculation purpose, we will not utilize that capacity. So there must be a cutoff line, and that cutoff line is being given to us by the ACI code. The ACI code has very categorically mentioned in the section 21.2.2 that the nominal strength of a member that is subjected to moment or combined moment and axial force is determined for the condition where the strain in the extreme compression fiber is equal to the assumed strain limit of 0.003. Strains at stage 3. In other words, the member finally fails by crushing of concrete even if steel and tension is yielded well before crushing of concrete. This is very important to understand. इसमें जो समझने की बात है वो ये है कि स्टील यील्ड हो गया लेकिन कंक्रीट क्रश नहीं हुआ, तो आपके पास इक्वेशन है Mn इज इक्वल टू ASFY माइनस A बाई 2. उससे आप Mn मालूम कर सकते हैं बिकॉज Fs इज इक्वल टू Fy कर सकते हैं. लेकिन स्मॉल a जो है स्मॉल a में ASFY डिवाइड बाई 0.85 प्राइम सी बी है. अब उधर FC जो है स्टील तो यील्ड कर गया, लेकिन FC की जो वैल्यू है जिससे आपने स्मॉल a मालूम किया वो 0.85 प्राइम सी नहीं है. मेरी बात आप समझ रहे हैं? नीचे स्टील तो यील्ड हो गया, लेकिन स्मॉल a में जो उधर स्ट्रेस है FC, तो अगर आप इस स्टेज पर कैपेसिटी मालूम करना चाहते हैं कि आपका स्टील तो यील्ड कर गया लेकिन ऊपर अभी Fs इज इक्वल टू 0.85 प्राइम सी नहीं, तो आप उस करस्पॉन्डिंग स्टेज के लिए स्ट्रेस मालूम कर लेंगे. आप स्ट्रेस मालूम करें और उससे स्मॉल a मालूम करें और फिर आप उस करस्पॉन्डिंग स्टेज पे आप Mn मालूम कर सकते हैं. लेकिन अगर आप के पास उस स्टेज के लिए FC की वैल्यू नहीं है तो फिर आप नहीं कर सकते। स्मॉल ए विल बी अननोन टू यू। मेरी बात आप समझ रहे हैं? अब आपने मजीद लोड डाला और स्टील यील्ड हो गया और उधर स्ट्रेस भी बढ़ गया, और स्ट्रेस इतना बढ़ गया कि जो एक्सट्रीम फाइबर हैं कंक्रीट में उसमें स्ट्रेन 0.002 हो गया। तो इसके करस्पॉन्डिंग भी आप mn मालूम कर सकते हैं। बात समझ रहे हैं आप? इसके करस्पॉन्डिंग भी, और स्ट्रेन की कोई और वैल्यू आ गई तो उसके करस्पॉन्डिंग भी आप मालूम कर सकते हैं। तो कौन सी कैपेसिटी आप लेंगे? या स्टील यील्ड नहीं कर रहा, स्टील यील्ड नहीं कर रहा, स्टील की क्वांटिटी बहुत ज्यादा है और कंक्रीट में स्ट्रेस बढ़ता जा रहा है और स्टील में भी स्ट्रेस बढ़ता जा रहा है, लेकिन स्टील यील्ड नहीं कर रहा, और कंक्रीट के ऊपर क्रश हो गया, 0.003 तक स्ट्रेन पहुंच गया, वो हो गया, लेकिन स्टील अभी यील्ड भी नहीं हुआ है। तो अब ये कैपेसिटी आप इसके करस्पॉन्डिंग आप कौन सी कैपेसिटी किस तरह मालूम करेंगे? ये कैपेसिटी आप लेंगे कि नहीं, मजीद लोड डालेंगे ताकि स्टील यील्ड भी हो जाए? मेरी बात आप समझ रहे हैं कि नहीं? तो आप कौन से स्टेज पे लेंगे? तो एशियाई कोड ने एक क्राइटेरिया बनाया है, वो कहता है आप स्टील के यील्ड को नहीं देखेंगे, आप स्टील के यील्ड को भूल जाएं। यू विल लुक एट द क्रशिंग ऑफ कंक्रीट। कंक्रीट ऊपर क्रश कर गया, स्टील अब बीम दो टुकड़े नहीं होगा, बीम दो टुकड़े नहीं, क्योंकि स्टील तो नीचे मौजूद है, वो तो अभी यील्ड पर ही नहीं गया हुआ है। अगर ऊपर क्रश भी कर जाए तो क्रशिंग के बाद जब आप लोड डालेंगे फिर अब ये ऊपर तो कंक्रीट ले नहीं सकता है, तो फिर अर्थ सेक्शन से क्या होगा कि ये स्टील अब यील्ड होगा, जैसे कि आपने टेंशन टाइजर लगाई हो और ऐसे कंप्रेशन स्ट्रट दो आ गए, क्योंकि बेंडिंग मोमेंट कपल तो खत्म हो गया ना, कपल तो खत्म हो गया, क्योंकि जब कंक्रीट ऊपर क्रश हो गया तो कपल खत्म, देयर इज नो सी नाउ, देयर इज नो सी बट देयर इज टी। तो आप लोड कैसे ट्रांसफर होगा? आप अर्थ सेक्शन से लोड ट्रांसफर होगा। जब आप लोड डालेंगे तो इधर एक कंप्रेशन स्ट्रट दो बन जाएंगे और इधर टेंशन बन जाएगा, तो ये अर्थ सेक्शन से और भी लोड ले सकते, काफी लोड लेगा। बट द एशियाई कोड वो आपसे कहता है कि ये आप ये स्टेज आप नहीं डिस्कस करते हैं, बस कंक्रीट क्रश कर गया, खत्म, बस ये मेरा स्टेज है जिसपे आपने mn मालूम करना है। आप स्टील यील्ड कर गया है नहीं, वो अलग बात है। बात समझ रहे हैं आप? अगर स्टील यील्ड नहीं कर गया और कंक्रीट ऊपर क्रश हो गया तो फिर आप F F नहीं ले सकते, बल्कि आप Fs मालूम करेंगे। कैसे मालूम करेंगे? स्ट्रेन से आप Fs मालूम करेंगे, स्ट्रेन डायग्राम से आप Fs मालूम करेंगे और उस Fs से आप mn मालूम करेंगे। मेरी बात आप समझ रहे हैं कि नहीं? You are now MSc students, you must understand these things. There can be another condition कि yield और crushing दोनों simultaneously हो रहे हैं, ये मुमकिन है, तो उसमें तो कोई मसला नहीं है। स्ट्रेन ऊपर 0.003 तक पहुंच गया और F F5 आ गया, तो इस कंडीशन के लिए आप मालूम कर सकते हैं। एशियाई कोड कहता है कि आप नॉमिनल कैपेसिटी मालूम करेंगे mn उस वक्त कि जब कंक्रीट ऊपर क्रश कर जाए, बल्कि क्रश न करे, स्ट्रेन 0.003 तक पहुंच जाए। टू बी वेरी स्पेसिफिक, क्रशिंग की बात नहीं कर रहा। वो कहता है कि एक्सट्रीम फाइबर में ऑन द कंप्रेशन साइड जब स्ट्रेन 0.003 तक पहुंच जाए तो बस ये कंडीशन है, इससे मैं ज्यादा कैपेसिटी नहीं लूंगा। mn जब आप मालूम करेंगे तो उसमें ये अंडरस्टूड है कि कंक्रीट कंप्रेशन साइड में 0.003 तक पहुंच गया। स्टील के साथ क्या हुआ है? इट विल डिपेंड ऑन द अमाउंट ऑफ स्टील। बात समझ रहे हैं आप? In other words, the member finally fails by crushing of concrete even if steel and so when we say that the member finally fails, तो for the purpose of calculation मैं कह रहा हूं, एक्चुअल नहीं। मेरी बात आप समझ रहे हैं कि नहीं? यानी मेंबर हम फेल कंसिडर करेंगे, उसके बाद अर्थ सेक्शन लेता है, कुछ भी करता है, बस फॉरगेट अबाउट दैट, हम वो लेते ही नहीं कैलकुलेशन। हमने बीम एक्शन से हमारा कपल खत्म हो गया, क्रशिंग खत्म, बस आपने ये mn मालूम करना। ओके, now the possibilities, we will quickly go through these because you already know this. There can be a balance failure condition when strain and steel is equal to yield strain, and when concrete crushes and at F is 0.003 depending on the amount of steel present as tension, following conditions are possible. जब ऊपर कंक्रीट 0.003 तक पहुंच गया तो नीचे तीन मुमकिन, तीन पॉसिबिलिटीज हैं। वन इज दैट उसी वक्त जो है स्टील यील्ड करे, द अदर इज कि स्टील अभी यील्ड से बहुत कम हो, और दूसरा ये कि स्टील का जो स्ट्रेस है वो यील्ड से यानी स्टील यील्ड कर गया है। तो आमतौर पे आपको पता है हम तीसरे कंडीशन के लिए डिजाइन करते हैं, फर्स्ट टू कंडीशन के लिए हम डिजाइन नहीं करते। और फॉर रिलेटिवली हाई अमाउंट ऑफ टेंशन रिइंफोर्समेंट failure may occur under conditions 1 and 2, causing brittle failure. It is for this reason that ACI code restricts maximum amount of enforcement in limit applicable to flexure level. You know this. अब ACI code wants to make sure that the failure is ductile, क्योंकि ये हम पहले लेक्चर में पढ़ चुके हैं कि फेलियर की पॉसिबिलिटी या प्रोबेबिलिटी को आप बिल्कुल खत्म नहीं कर सकते. If you remember in lecture number 1, we have statistically proved that it is not possible to completely eliminate the chances of failure of a member. You cannot do this. ठीक है जी, कम ज्यादा आप कर सकते हैं, 10% तो आप 1% पे ले आए, लेकिन आप बिल्कुल जीरो नहीं कर सकते. It is statistically not possible. So if there is a chance of failure, we would like that the beam fails according to our choice, and our choice is ductile. And the beam fails in a ductile manner. The beam has to fail. It should fail in a ductile manner to give us a escape time. ठीक है जी, हमें escape time मिल जाए और लाइफ सेफ हो, तो उसके लिए हमें एक ductile behavior चाहिए. तो ductile behavior के लिए there are several ways. In the ACI 318, in the codes earlier than the ACI 318 2002, 2002 से पहले के कोड में ACI कोड ने इसको कैसे इस मसले को हैंडल किया था, उसने इसको ऐसे हैंडल किया था. उसने कहा था कि आप रो बैलेंस मालूम करें, और रो बैलेंस आप आराम से मालूम कर सकते हैं. यानी वो अमाउंट ऑफ रिइंफोर्समेंट कि जो आप डालेंगे तो कंक्रीट ऊपर क्रश कर जाए और स्टील यील्ड कर जाए जी, वो अमाउंट ऑफ रिइंफोर्समेंट आप मालूम करते, किसी सेक्शन के लिए मालूम कर सकते, कोई मसला तो नहीं है. इसको आप कहेंगे बैलेंस रिइंफोर्समेंट. क्या कहेंगे? बैलेंस कंडीशन, यानी वो रिइंफोर्समेंट जो कि बैलेंस कंडीशन पर हो. And then you should put a restriction on the amount of reinforcement that will be actually placed. How? That, okay, I will not allow the amount of reinforcement more than 75% of the balance. यानी कि मैं 75% of the balance से allow नहीं करूंगा. तो जब उससे कम होगा तो जाहिर है कि स्टील पहले ही करेगा. This was the approach before 2002. Up to ACI 31899, this approach was followed. Here we would calculate row balance, and row max was calculated as 0.75 times row 2. This was the approach. But after 2002, this was a drastic change in the code. That for the first time, the code changed this concept, and the code now handles this issue in another way. The code says that, okay, the strain on the tension side in the steel, shall be equal to or more than 0.005. That the amount of reinforcement, whatever amount of reinforcement is placed on the tension side, it shall be such that strain on the tension side in the steel is equal to or more than 0.005. So, if strain in the steel is 0.005, what will happen? You can see the stress strain diagram of the steel. This is a grade 40 steel. So, this is the yield strain for grade 40. This is the yield strain for grade 60. And this is 0.005 limit. So, by putting a restriction on strain, the code has made it sure 100% that the steel would have yielded when concrete on the compression side pressures. Because 0.005 is greater than the yield strain of grade 40 as well as of the grade 60 steel. If you look at the grade 60 steel strain, which is a value around here, this one. So it is around 0.002, and 0.005 is around double of 2.5 times of this, 2.5 times of the yield strain. So which will make sure that the steel on the tension side is yielded when concrete on the compression side pressures. So the code now says that the strain in the steel on the tension side must be more than 0.005. And for the first time, the code has now introduced in 2002 this kind of graph, which says that, okay, the flexure, the flexural strength reduction factor